Okay, so good evening. This is the eighth live discussion session of the course Geotechnical Engineering 1. This course was actually scheduled to happen on last Friday, that is the 14th, but due to some unavoidable circumstances, it has been uh, postponed. So, in yesterday's class, I believe the Bosing's theory has been applied, has been taught. So I'll just go to the PPT right now. Just a moment. Yes. So this is the PPT. Yes, I believe the PPT is being recorded right now. So in the previous class, I think I had told you about the Bosing's theory. In this class, the topic is flow nets, stresses in soil from surface loads. Flow nets is a part of the seepage analysis which was done, I think, in the 7th week, I believe, isn't it? Seepage analysis was done in week 7. Hello? Seepage analysis was done
Yes,
in
sir.
week 7, right? Yeah. So,
Yes, sir.
yes, so some parts, some bits of the concepts and problems will be there here also, and also a generalized view on the stresses in soil from the surface loads will also be there. Like the other sessions, it will also have MCQ, true false statements, and numericals. So I hope you know the procedure, and without further ado, I'll just the start dictating the questions. Okay. So again, good evening. This is the eighth discussion session, Geotechnical Engineering 1. The topic of today's discussion is flow nets, stresses in soil from surface loads. Okay. So the first question is stresses due to self weight are also known as stresses due to self weights are also known as first option static stresses, second option gravity loads, third option geostatic stresses, last option effective stresses. I repeat the question. Stresses due to self weight are also known as first option static stresses, second option gravity loads, third option geostatic stresses, last option is effective stresses. Okay. Okay. So next question. Contour joining points of equal vertical pressure below the ground is called contour joining points of equal vertical pressure below the ground is called? First option, iso height. Second option, isobar. Third option, isochrone. Last option is none of these. I repeat the question. Contour joining points of equal vertical pressure below the ground is called. First option, iso height. Second option, isobar. Third option, isochrone. Last option is none of these. Okay. Next question. The Poisson's ratio for elastic materials varies between. The Poisson's ratio for elastic materials varies between. First option 1 to 2. Second option 0 to 1. Third option 0 to 0.5. Last option 0.5 to 1. I repeat the question. The Poisson's ratio for elastic materials varies between first option 1 to 2, second option 0 to 1, third option 0 to 0.5, last option 0.5 to 1. Okay. Okay. Next question. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. I believe this question will be easy for you because after solving the numericals from the previous class, last class, anyway, this question was already framed, so I have not removed it. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is, first option 1.22, second option 0.86, third option 0, last option 1.62. So no one else has joined. I believe they're attending the other session, right? The other session. Have you joined the other session, or you're just joining this session?
Last class I was there, sir.
Not last class. Right now another session is going on, right? 5 to 7.
5 to 7 actually I opened and nobody is allowing me, sir. Actually,
Oh, okay, okay, okay. That is not good. Okay, fine.
yeah.
Anyway, yeah. I repeat the question. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is, first option 1.22, second option 0.86, third option 0, last option 1.62. Okay. Next question. Yes. Which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? I repeat, which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? The options are, first option is stream function, second option is scalar velocity, third option potential function, last option is velocity potential. I repeat the question, which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? First option stream function, Second option, scalar velocity. Third option, potential function. Last option, velocity potential. Next question. Westergaard's formula for vertical stress gives a greater value of stress than that by the Boussinesq formula when R by Z exceeds. Westergaard's formula for vertical stress gives a greater value of stress than that by the Boussinesq formula when R by Z exceeds. First option 1.12, second option 1.52, third option 2.22, and last option is 2.62. I repeat the question. Westergaard's formula for vertical stress gives greater value of stress than that by the Boussinesq formula when R by Z exceeds. The options are 1.12, 1.52, 2.22 and 2.62. Okay? Now, next question. The zone within a soil mass bounded by a contour of constant vertical pressure intensity is called. The options are stress zone, pressure bulb, stress bulb, or none of these. I repeat the question. The zone within a soil mass bounded by a contour of constant vertical pressure intensity is called. Your options are stress zone, pressure bulb, stress bulb, or none of these. Next question. A combination of velocity, potential and stream function is called. A combination of velocity, potential and stream function is called. First option, combined function. Second option, stream velocity potential. Third option, complex potential. Last option, none of these. I repeat the question. A combination of velocity potential and stream function is called. The options are combined function, stream velocity potential, complex potential, or none of these. Next question. In the case of anisotropic soils, the flow net is drawn for the transformed section, which is obtained by reducing the horizontal dimensions and keeping the vertical dimensions unchanged. Is this statement true or false? Vertical dimensions unchanged is not something, you know, significant, so significant in all the cases. Sometimes they are, but in majority, what do? Do we need to reduce the horizontal dimensions or transform them or not? So is this statement true or false? I repeat the statement. In the case of anisotropic soils, the flow net is drawn for the transformed section, which is obtained by reducing the horizontal dimensions and keeping the vertical dimensions unchanged. Is this statement true or false? And you can say if it is true, how it is changed. If it is false, then it is fine. If it is true, you have to say how it is changed. Anyway, next question. A stress theory suitable for stratified soil is. A stress theory suitable for stratified soil is. First option, Buznik's theory. Second option, Newmark's chart. Third option, Westergaard's theory. Last option, none of these. I repeat the question. A stress theory suitable for stratified soil is. The options are Bojin's theory, Newmark's chart, Westergaard's theory, or none of these. Next question. The shape of a field is approximately a, you know what is the field? I think I have mentioned in the session on
Yes,
wave
sir.
cycle. Yes, what is the field?
It is a intersection of two successive equipotential lines and flow lines gives a flow field.
Yes, flow field, very good. So the shape of a field is approximately a, first option rectangle, second option square, third option circle, last option hexagon. I repeat the question. The shape of a field is approximately a, first option rectangle, second option square, third option circle, last option hexagon. Just a moment. Yes, I hope we have written this question. Sorry for the interruption. Okay, next question. Quantity of water flowing through each flow channel is the same. Is this statement true or false? quantity of water flowing through each flow channel is the same. Is this statement true or false? Next question. The Westergaard's influence factor is a function of, first option r, that is the radial distance from the axis of loading. Second option z, that is the depth. Third option both of these, and last option none of these. I repeat, the Westergaard's influence factor is a function of, first option R, second option Z, third option both of these, last option none of these. Okay. Okay, just a moment. Let's place one over here, and I think this one has, anyway, let me do this for the sum. This has a solution. Okay, fine. So this was the last question. Yes. Okay. Next question. You can draw the diagram or you can take a screenshot of it, whatever is comfortable. A water tank is supported by a ring foundation having outer diameter of 10 meter and inner diameter of 7.5 meter. The ring foundation transmits uniform load intensity of 160 kilonewton per meter square. Following Westergaard's analysis, taking Poisson's ratio as 0, taking Poisson's ratio as 0, compute the vertical stress induced at a depth of 4 meter below the center of the ring foundation. The outer diameter is 10, the inner diameter is 7.5. I repeat the question. A water tank is supported by a ring foundation having outer diameter of 10 and inner diameter of 7.5 meter. The ring foundation transmits uniform load intensity of 160 kilonewton per meter square. Following Westergaard's analysis, taking Poisson's ratio as 0, compute the vertical stress induced at the depth of 4 meter below the center of the ring foundation. The diagram has been shown. Okay, next question. Yes, this question, please write down the data very carefully. You might need to, draw the diagram for it also. Anyway, this is from seepage analysis, flow net seepage analysis. Yes. An earthen dam rests on an impervious foundation. The relevant data is given below. Height of dam is 58 meter. Freeboard is 1.5 meter. The upstream slope is 2.75 is to 1. The upstream slope is 2.75 is to 1. Okay. Horizontal to vertical. Downstream slope in the same way it is 2.5 is to 1. Upstream is 2.75 is to 1. Downstream is 2.5 is to 1. Crest width is 6 meter. Length of the drainage blanket below the downstream side, it is 110 meter. The coefficient of permeability of the embankment material in the horizontal direction, it is kx equals to 4.5 into 10 to the power minus 7 meter per second, and ky, that is in the vertical direction, it is 2 into 10 to the power minus 7 meter per second. Determine the seepage through the earthen dam. I repeat the question. An earthen dam rests on an impervious foundation. The relevant data is given below, where height of the dam 58 meter, freeboard is 1.5 meter, upstream slope is 2.75 is to 1, downstream slope is 2.5 is to 1, horizontal to vertical in both the cases. Crest width is 6 meter, length of the drainage blanket is 110 meter. The coefficient of permeability of the embankment material in the x direction, kx equals to 4.5 into 10 to the power minus 7 meter per second, and ky equals to 2 into 10 to the power minus 7 meter per second. Determine the seepage through the earthen dam. Okay. Next question. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of vertical pressure at a depth of 10 meter below the ground surface and situated at the axis of loading. What will be the vertical pressure at a depth of 5 meter and a distance of 2 meter from the axis of loading? Use Westergaard's analysis. I believe we have solved this sum yesterday using the Bosing's analysis. This one or something very similar to this. So today you have to solve this using the Westergaard analysis. I repeat the question. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of vertical pressure at depth of 10 meter below the ground surface and situated at the axis of loading. What will be the vertical pressure at a depth of 5 meter and at a distance of 2 meter from the axis of loading? Use Westergaard's analysis. Okay. Next question. The base dimensions of flow net are 4 meter and 3 meter for natural and transformed sections respectively. What is the anisotropy ratio? This is for just one dimension, the base dimension, which is essentially, I am just telling you, it should be horizontal. Okay. So the base dimensions are, for the natural section it is 4 meter, for the transformed section it is 3 meter. So from this you have to calculate the anisotropy ratio. Is this question clear? Is the question clear? Are you there in the meeting? Yes. Any doubt regarding this question? Okay, anyway. Yes. You want to say something? Any doubt you have?
No, sir, we'll see it.
Okay, okay. Last question. For a sheet pile wall constructed in a soil having effective grain size 0.1 millimeter, the difference of the upstream and downstream water levels is 3 meter. If the flow net drawn for the problem yields 2 as a ratio of the number of head drops to the number of flow channels, then what is the discharge in unit of meter cube per second per meter length of the sheet pile wall? The question is a bit long, you can write it or just take a screenshot. Take a note that the effective grain size is given, effective diameter of the soil particles. is given as 0.1 millimeter. Difference of the upstream and downstream water levels is 3 meter. The ratio of the number of head drops to the number of flow channels is 2. Find out the discharge. I repeat, for a sheet pile wall constructed in a soil having effective grain size 0.1 millimeter, the difference of the upstream and downstream water levels is 3 meter. If the flow net drawn for the problem yields 2 as the ratio of the number of head drops to the number of flow channels, what is the discharge in unit of meter cube per second per meter length of the sheet pile wall? Okay. So these are the questions. I'll give you how much? 10 minutes. I'll start at 7:05 to 7:07, something like that. Will it be okay? 7:05 to 7:07. I'll start. Okay, fine. Okay, I hope you have solved the questions. I'll start discussing. Sorry. Okay. So the first question was stresses due to self weight are also known as. What is the answer?
C, sir. Geostatic stresses.
Yes, good. Geostatic stresses in any geotechnical material, soil, rock, whenever you talk about geostatic stresses, that is the stress due to self weights. Okay. Next question. Yes. Contour joining points of equal vertical pressure below the ground is called. What is the answer?
Isobar, sir.
Isobar. Yes, isobar is the correct answer. So, what is an iso height?
Line joining the points of equal precipitation in
Precipitation.
hydrology.
Yes, an isochrone.
Line joining the points of hydrodynamic pressure.
Hydrodynamic pressure.
Yes, sir. U bar in consolidation chapter.
Yes, that is also one isochrone, but generally in hydrology also there is a definition. The travel time will be same, like the time taken for water to reach a certain point. Okay, in hydrology, okay, the point joining the same time taken for the flow of water to reach a certain point in the watershed is also called isochrones. There is also definition. Okay,
Okay.
know
On the
that one.
water catchment area.
Yes, yes, catchment area. Right, right,
Okay,
right. That is
okay,
also
sir.
definition. Okay. So in this question, contour joining points of equal vertical pressure below the ground. The answer is isobar. Okay. Okay. Just a moment. I'll just go on saving after each and every slide. Otherwise, something might happen like yesterday. Okay. So isobar is the answer. Next, this question. Poisson's ratio for elastic materials varies between. What is the answer?
0 to 0.5, sir.
Yes, 0 to zero point 0.5. Zero point 0.5 will be the maximum value. Poisson's ratio means ratio of the lateral strain to the longitudinal strain or diametric strain to the axial strain. For elastic materials, it lies between 0 to 0 0.5. Good. Next question. Yes. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. What is the answer?
0, sir.
Yes, 0. because it is directly below the point load, so the radial distance is 0. So whatever the value of normal stress sigma z is, sigma z, the radial stress tau will be equal to sigma z into r by z, isn't it? Sigma z into r by z. This r equal to 0. Hence, the value of tau will be also equal to 0. Okay. 0 radial distance, so radial shear stress equal to 0. Okay.
Sir,
Yes.
is the R by Z can be greater than 1 and less than 1 possible, na, sir? Equivalent to 1 also possible.
Yes. That is, I have
Okay.
given one question, right? I'm coming to the more than one also possible. Yes, because depth, suppose the depth is 5, radial distance is 2, r by z is less than 1. Okay,
Less than 1.
but we have to calculate, suppose the depth is 5 and radial distance is 10. Although in such cases, the value of the shear stress will be very low in such cases, but still we'll get some value. So it can be less than or more than 1.
When these two are equal, R and Z are both are equal, then tau and sigma Z also will be equal.
Yes, exactly. That's a very good
Okay.
observation, right? Tau and sigma will be equal when r equal to z. Exactly. Very good
Okay,
observation.
sir.
Yeah. Next question. Which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? What is the answer?
I am not sure, sir, about this topic, but maybe potential function. I am guessing.
No, it is stream function. Previous
I need.
class, in the week 7, I have given a similar question with a different definition for the velocity potential. Now I will show the definition of stream function. The answer is stream function. We represent this. You haven't heard about stream function, right?
No, sir. I am not comfortable with this topic. That's why
Okay,
I
okay,
directly.
okay. No issue. Stream function is this represented by xi. Now, there are two definitions I have found in fluid mechanics and soil mechanics. With respect to the seepage analysis in soil mechanics, the direction they mention, I will go by that. Okay. So I have mentioned over here partial derivative with respect to any direction. Suppose this is the x direction, right? This is the y direction, and this is the negative x direction. This is the negative y direction. Okay. So when we talk about partial derivative of this function with respect to, suppose, x direction, so I have said to any direction gives the velocity component perpendicular. So I am doing with respect to this x direction, what will happen is it will go like this clockwise. Okay, this partial derivative will transform it clockwise into a velocity function that is negative vy. Okay. Similarly, if I do the partial derivative of this function with respect to y, what will happen? What will
It
it give?
becomes Vx.
Vx, very good, Vx. Okay. This clockwise and anti-clockwise concept and funda, this kind of, I've seen it fluctuate, in soil mechanics and some textbook of fluid mechanics, but in standard books of soil mechanics with respect to this seepage analysis, this is the standard definition I have got. Okay. So yes, a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction. It is called a stream function. Okay, of course, this stream function and velocity potential, these kind of numericals, they don't generally gel with the problem of seepage analysis in soil mechanics, but in fluid mechanics, you will find problems with respect to these concepts. Okay.
Is the concepts and examples are same, sir, in soil and water?
Yes, concepts are same. Concepts are same. Just I have only one hitch which I have not yet seen anywhere getting solved. There is
Yeah.
this clockwise and anti-clockwise. The concept in both the cases are same. Okay, you perform a
Okay.
differentiation, partial differentiation, you get the velocity. Okay, concept is same, but
Okay.
this clockwise anti-clockwise direction, there might be some uh, how to
Mhm.
say, difference in opinion in some, for some
Okay.
author, between some authors. Okay, anyway, the answer is stream function. Okay, okay, I'll save it again. Yes, next question. Westergaard's formula for vertical stress gives greater value of stress than that by the Bosing's formula when R by Z exceeds. What is the answer?
1.5 to sir. B.
Yes, you know the chart, right? When
Yes, sir.
KB is always more than KW, isn't it?
Mm.
But
Yes.
when that R by Z value, it goes past, uh, so this is this is suppose K, which represents KB and KW. This is R by Z. So this is like this, and this is KB. Okay, this point where this graph, that is KB and this is KW, it is, this point is 1.52. Then KB reduces, KB gets reduced. And anyway, we know, I have told about stress, greater value of stress. We know the stress formula is factor into load by Z square, right? Any factor, either KW or KB, into load by Z square. So this factor, if it gets reduced, the stress automatically gets reduced. Okay, then the other one. So generally KB is more than KW. Once it goes past this gap 1.52, then otherwise more than 1.52, then KW gets more than KB over here. KW is more than KB. Okay, good. So when R by Z exceeds 1.52, Westergaard's formula will give a greater value of stress than the Bosing's formula. Okay, next question. A zone within a soil mass bounded by a contour of constant vertical pressure intensity is called. What is the answer?
Pressure bulb, sir.
Yes, pressure bulb. If you see from the top view, like these are the points where you have equal, constant vertical pressure in these points due to any load. If you join this, the zone you will get is called a pressure bulb. It can also be vertical for some loads like this. The same pressure is also over here. Okay, because you know Westergaard's, it takes the concept of stratified soils also. I have discussed it in the next question. So this zone will be called as a pressure bulb, not a stress bulb, but pressure bulb. Okay. Anyway, okay. So next question. Yes, here's a very easy question. Combination of velocity potential and stream function is called. I think you are not comfortable with this topic, right?
Yes, sir. Yes, sir.
Yes. Okay. So it is called a complex potential. Complex number, combination of real and imaginary numbers. So this complex potential represented by W. It is a combination of real value, that is the velocity potential, which I have mentioned in the session 7, and imaginary number multiplied by with the stream function. This is called a complex potential. This is generally not of any use because just a definition. I have not seen this particular thing being applied over here, but it might be in some scenarios. Anyway, it is always good to know. So combination of velocity potential, that is phi. Oh, sorry. And velocity potential, this is called the phi, and stream function, this is xi. It's called complex potential. Okay.
Sir, last time I asked which textbook is good for this topic.
Which textbook is good for this topic?
As per your
My
knowledge.
recommendation will always be BC
Discipline.
Punmi. Yes, yes.
Okay,
You know,
okay. I will go through, sir.
learn the basics, solve the numericals always,
Okay, sir. I will go through.
and even it is good for competitive exams. I have seen many gate questions, civil
Yeah, yeah,
services
I have
questions.
seen. I am following that all.
Yes, yes. So that
Only
book,
this topic I am not familiar.
this topic is explained, means whatever you need to know, the basics, for
Hmm.
solving problems with respect to velocity potential, stream function, complex potential. I would suggest you to follow a fluid mechanics book. Okay, I think
Which author, sir? Which author
I
again?
have to check. I think RK Bansal. I think RK
Bansal is okay.
Bansal. Yes,
Mechanical engineering book it
yes,
is.
yes, yes. Fluid mechanics
Okay.
book. That part, and that book
Yeah.
is a very good book for fluid
I
mechanics.
will. I will. I will go through, sir.
Yes, so this part, and also compare from that book and the BC Punya book, this part, velocity potential and stream function,
Okay.
and see if you find any discrepancies. Okay,
Okay, sir.
okay,
Hmm.
yeah,
Thank you, sir.
yeah. Okay, so next question. In the case of anisotropic soil, the flow net is drawn for the transformed section, which is obtained by reducing the horizontal dimensions and keeping the vertical dimensions unchanged. Is it true or false?
It is true, sir.
Yes. So how do we change that?
Actually, for anisotropic soils, the flow net is looks like a rectangle. It is not flow field is a rectangle.
Hmm.
So when you transform the section, we are going to reduce the horizontal dimensions
Yes. So this is
so
K.
that it becomes a square.
Yes. So Kx and Ky being the coefficients of permeability in x and y direction. Okay. So when we take a transform value, and this I am doing with respect to Kx only. You can do it with any dimension like x, okay, L, with any horizontal dimensions, anything horizontal. I am just doing the generalized value. While transform value of Kx we take to find out the seepage. You know the formula, right? Q equals to what? Q equals to Kh into Nf by Nd, isn't it? Kh into Nf by Nd. So K should be 1, singular value of K. We should not find out in both the cases in vertical, because when we talk about you know flow through soil, generally horizontal direction we consider. Quicksand condition, seepage in upward direction, those are special cases. Okay, so this value of K, this transform value of K in the horizontal direction, how do we solve this? The actual value in the horizontal direction multiplied by root over of how much, you know root over of Ky
Vertical direction by
by
horizontal
horizontal
direction.
direction. Yes, so this value we get over here is the transform value of the permeability coefficient in the horizontal direction is this one. Okay, so yes, it has to be reduced keeping the vertical dimensions unchanged. This is a true statement. Good. Next question. A stress theory suitable for stratified soil. Very easy question. Which one?
Westergaard's theory, sir.
Yes, Westergaard's theory. Next question. Shape of a field is approximately a, again easy question.
Square.
Yes, square. So generally they are curved lines. It may initially look like a rhombus, but it is actually a square. If you remove the ignore the curved lines, it's actually a square. B equals to L. Okay. Next question. Quantity of water flowing through each flow channel is the same. True or false? Again, easy question.
True, sir.
Yes, quantity of water flowing through each flow channel is the same. This is the way we can actually, it makes us easier to solve the problems. Uh, Otherwise, we have to consider each flow channel differently, count the number of flow channels, and then solve the sums and find out the discharge. Anyway, this is a true statement. Next question. Westergaard's influence factor is a function of R, Z, both, none. What is the answer?
Both of these.
Yes, both of these. What is the formula for Westergaard's influence factor? Please tell me.
1 by pi
Yes.
in bracket, whole bracket.
Hmm. I'm using, if I use the Poisson's ratio equal to 0, then I guess 2 comes out, isn't it?
Yeah,
R by
that's
Z
all.
whole square whole to the power,
Two times r by z whole square,
yes,
whole
2,
to the power of 3 by
yes,
2.
2 times R by Z whole to the power 3 by 2. This function of both R and Z. Okay. If that factor Poisson's ratio was also there, then it would have been all of the above, because Poisson's ratio is counted over here. It is
Hmm.
actually 0. If we do it 0, then we get 2 over here. Okay.
Same question valid for even Bosniak's theory also, sir.
Yes, if it was Bosnian's influence factor also, this would have been the same. Okay,
Same question. Okay.
same, yeah. Okay, next question. Have you solved this? And if you have, how have you solved this?
Yes, sir. Answer is 22.29 kPa.
Not matching. Not matching.
Not matching, sir.
No.
Okay. Okay.
So just
I
check.
will check out.
Yeah, just check once. I believe for the first case, for the outer one, it will be R0. Okay, so the load is same in both the cases. Okay, so I'll just write the expanded formula so that you can understand. So Q into 1 minus 1 divided by 1 plus 2 into R0 outer one by Z whole square, and this one has to the power half. This is the outer one, outer load, minus again Q into, you can take Q common also outside and then do the sum, you can do it easily. 1 by 1 plus 2 into radius inner one divided by Z whole square 1 by 2. Is this the formula you have used or something else?
I have used cos cube theta, 1 minus cos cube theta.
But cos cube theta, is it applicable in Westergaard? How are you getting cos cube over here? Because in the case of
Okay.
Bosing's theory, it was 3 by 2.
Okay.
Okay, then you are getting cos cube, but it is 1 by 2. Okay,
I
so
forgot the Western Ghats theory.
it is Westergaard's theory. That is the thing. Okay, so using
Yes,
this one,
that's why I didn't get
yeah.
it.
Okay, so you use the Bosing's formula, right?
Yes, sir. By
Okay,
mistake, I
no,
have
no,
done it.
it's okay, it's okay. But you should use the Westergaard because it has been mentioned over here, following the Westergaard analysis.
Mhm.
Okay,
Okay.
I know
Okay.
Bosing's theory is much easier. We have shortcut formulas. Anyway, so Q, the value of Q, we have how much? It is 160.
Mistake, so that I can learn now here.
Yes, yes, of course. If you don't make mistake, how will you learn? Q is 160. R0. What is the value of R0? R0 is 5, right? Outer one diameter is 10. So this radius will be equals to 5 meter. I'm not writing the units. Ri, what is the Ri value? It is 7.5, so it will be 3.75. 3.75. And value of Z in both the cases, I have asked to find out at a depth of 4 meter, so it is 4. Okay, so just put the values in the equation. The first part, I think the outer load will be approximately equal to something around 81.22, and the inner load will be approximately equal to something around 63.65. You subtract this, you will get something around 17.57. Is this something you are getting by subtracting? Yes, this is the value after subtracting in kilonewton per meter square or kPa, whatever. Okay, So I think it is clear to you that how to solve this using the Westergaard formula.
It is clear, but small clarification needed, sir.
Yes,
Sigma z is equal to q into, in bracket you have written that 1 minus 1 by 1 something. Is
yes,
it a
yes.
influence factor?
This is the influence
Is it a
factor.
influence factor by Westergaard, sir?
This is the influence factor. Okay. This is the modified equation using the circular formula. Just a minute. I'll just tell you.
Okay.
Yeah. Actually, everything cannot be written in the notes, you see. So, something also needs to be written down from the book. So, that is the thing. I have to check the book and let you know vertical pressure from Westergaard's theory. Westergaard's analysis. Yes, this is the generalized formula for circular load. Generalized formula for circular load, K into Q. Okay, the value of K transformed is A divided by eta by Z. Eta has, you know, Poisson's ratio whole square. This entire thing. Okay. Yes. Yes. So same thing over here. This 1 minus the entire thing can be considered as the influence factor over here. Even though there is no z square is being taken over here. Okay, this entire thing will be taken as the can be taken. I think it can be taken as the influence factor based on the Westergaard analysis. Yes. Okay. So this is the outer load and this is the inner load.
Inner load. That
Inner
is clear,
load.
sir. That's,
Yes, this
yeah.
is the outer load and this is the inner load. So, and this is the generalized formula. Okay, it is not like it has
Okay.
been derived using the separate, you know, influence factor and this is the generalized formula of the Westergaard's. You can check the book, it will tell you. Okay, so I
I will
think
check,
it,
sir. So, sir,
yes,
if possible, can you write on side by Bosnick's formula? What is the inner value of that bracket?
Bosnick's formula, inner value.
Yeah, q into whatever you have written for Westergaard's. No, instead of that, if you write a
Okay,
Bosnick's,
you
what is
want
the
to solve it right now.
no need of solving, sir. Only that formula, whatever you have written just now
Formula. Okay,
in the other slide, solution slide,
solution slide
slide
like
number 16.
this one.
Yeah, yeah,
This one.
inner part of that bracket.
So you tell me what is the formula?
I forget, sir. I am using actually 1 minus cos cube theta. That is
1 minus cos cube theta. Okay, 1 minus cos cube theta you are using. So when you need to find out
instead of that
theta
in the form of r by z I want.
in the form of r by z you want. Okay.
Otherwise, I will refer it, sir. Last class you have done it. I remember yesterday.
Yes. Anyway, I'm just writing it
I
over
will
here.
I will go through.
Yes. Q into similar, very similar. 1 minus, and because it is similar, both together will be easy to remember. 1 plus a by z or r by z, whatever. Okay, so I'll just write, you want the inner one, right? So I'll just write ri, okay, by z, ri by z whole square, not considering the Poisson's ratio, hence not writing 2 on the outside. Okay, this is the difference. And here we have 3 by 2, this one. Okay, this one.
Okay. The comparison is only inside 2 times r by z. Here it is 1 times r by z.
Yes, and outside it is
That's you have
2 to the
written 2
power,
times r by z square.
yes, and outside this
Half and 3
factor,
by 2.
yes, half and 3 by 2. Okay, and even if it
Only
was,
these two
yes,
combinations.
and even if it was you know, 3 by 2 over here, then also I'm not sure, because you cannot use the cos formula because you have a twice of this.
I will work out, sir. Later I
Yes,
will
please
work out.
work this out, because trigonometrically this one can be converted to the cos cube formula. Okay, Whether this one can be converted,
Okay, okay,
we have to see. Okay, so this is the Bose-Einstein equation. Okay.
okay, sir. Done, sir. Uh, Thank you, sir. Today's mistake is good for me. Otherwise, somewhere I will do the same mistake.
Yeah, yeah. Okay, okay. Just need to just see the question carefully. Westergaard analysis. That's it. Okay.
Okay, okay.
Okay. Next question. Have you solved this one? Arden Dam?
No, sir. I think is it we have to use the Cauchy's formula for this
No, no, no.
focal length?
This
Uh,
is the problem from the flow net. From the
but
flow
FlowNet, we have FlowNet number of drops and all those are not given.
number of drops and all those are not given, but this one is different kind of problem. So okay, I'm just solving it for you.
Okay.
Okay. I first need
Okay,
to
sir. Thank
draw a diagram. Just a moment.
you. Yes.
Yes. Okay. So here I'll first draw the diagram. Just look at it very carefully. So this is an earthen dam. Okay, it has an upstream side, it has a crest, it has a downstream side. Okay, like this. And to prevent seepage or mm, that is excessive pore pressure, there is a drainage blanket filled with permeable soil in the downstream side. Okay, now in this question, first of all, height of the dam is 58. Okay, so I'll write over here height of the dam is 58. Freeboard is how much? Freeboard is
1.5 meters.
1.5. Yes, freeboard is 1.5 meter. The crest width is 6, I guess, isn't it? Crest width is 6 meter. Crest width
6
is
meter.
6 meter. Okay. Now the upstream, in the upstream, the horizontal to the vertical, the slope is 2.75 to 1, right?
Yes, sir.
And on the downstream side, the slope is 2.5 to 1.
It's to 1.
Yes. Now, the phreatic line that comes, okay, the topmost flow line, it comes like this, okay, and it has been assumed that this line can be extended to form a parabola. And this point can be C, and this is the parabola. This focus will be always at the starting of the drainage blanket. Okay, now if the parabola has a focus, it will also have a directrix. Okay, this is H, and this distance, this is called S, focus from the directrix S. Okay, so there is something empirical over here which we'll see, but this distance, that is D, from the focus till the point C, we assume it as from the point C, we assume it as D. We assume it as D. We take it as D. Okay. Now, from C to B, if this point is B, suppose the point where the phreatic line originates, C to B, CB will be equals to 0.3 L. Okay, and what is L? L is the horizontal projection of the upstream phase. That is, from B, if this part is A, if this end point, if it is A, and suppose it is A dash vertically, so AB will be equals to L. Okay, will be equals to L. Okay, now to solve the problem, the value of discharge is given by Q equal to, k times this s distance. S means from the focus to the directrix. Okay, this is the discharge formula in this case. Now there are some scenarios we have to consider over here. Firstly, we have to find out the value of s. What is the value of s? Isn't it? What is the value of s? The value of s is given by root over of d square plus h square minus d. Now d I have shown you, h is how much over here? The head causing the flow. So in this case the head will be how much? Tell me. 58 minus
freeboard.
1.5, that is 56.5, right?
Yes, sir.
56.5. So we have found out h. Okay, we have found out h. Now we have to find out d. How to find out d? I think we'll need another slide over here. Yes. To find out d, we have to add up. Few things we have to add up. So first of all, we will be needing this 0.3 into L, right? CB, distance we need. Okay.
Yes, sir.
Then this part, I think from after CB, wait a minute. Yes, this part, that is from B till this crest, we'll be needing. This is the first part, this is the second part, the crest part also will need the third part, and from here till the focus we'll be needing, isn't it? This is the entire distance
Yes.
of D. This is the fourth part.
Mm.
So now, up till this, from after this crest on the downstream side, if we take the entire downstream side, then we have to subtract the length of the drainage blanket, isn't it? Just that,
Yes, sir.
by that we can do it. So now I'll be writing over here the formula for D will be equals to, in this case, 0.3 L, the first part on the left side upstream, plus the part, horizontal part having the freeboard, that is
Freeboard, yeah.
multiplied by the slope. Okay, now comes the crest part. What is the crest value? 6. Okay, now on the in the downstream side we take the entire thing. Now the entire thing means the height multiplied by the slope, because in the downstream side there is no water, isn't it? There is no water, so no need of freeboard
Yes.
counting. So height multiplied by the slope, that is 2.5, isn't it? 2.5 is the slope. Now we taken the entire downstream side, we just subtract the length of the drainage blanket, 110.
110.
Yes, 110. Now what is the value of L? D we will find out. Okay, what is the value of L? L will be equals
20.5.
to, yes, how much?
I think 20.54.
20.54. No, it is the horizontal
No, sir.
projection. This is
Okay,
say,
okay, okay.
in this case L is the horizontal. What is the vertical value? 56.5, right?
Yeah,
Height
vertical
minus
is 1.
freeboard. Yes. So it will be the vertical height up till the water is there multiplied by the slope, that is 2.75.
0.7.
Now calculate this, you will find approximately, I think,
155.
155.38, right?
Yes, sir.
38 meter. Now put the value of this in the equation of D, you will get D equal to 91.74, I guess. 91.74 meters. Okay, 91.74 meters. Now we have kx and ky. So how can we find the equivalent value of k? Root over of kx into ky, right? Have you got the value of d?
1 minute. So I'll
Yes,
check.
yes. Just do it.
191 I am getting, sir. D.
Subtract 110 also.
Yeah, I have done, sir. 2 times I have done. I don't know. Once again, I will.
I'm getting 91.74.
Yes, sir.
91.74, right?
Yeah, I got it. Same. I got it.
Yes, good. So that is the value of d. Now to find the equivalent value of k in the horizontal direction, root over of kx into ky for this transform section, isn't it? So 10 to the power minus 7
Yes, sir.
remains constant, root over of kx is 4.5, ky is 2, gives us 9, so the value becomes k equals to 3 into 10 to the power minus 7,
Nice.
okay, meter per second. Now we have d, okay, we have
Yes, sir.
h, we have d, we have h. What is the value of s now? Find the value of s.
Approximately 1.6.
16. Yes, so I'll take the whole number 16 over here. S is 16. Okay, s is 16. So now the value of q equals to k into s. We have k3, that is 16. So it will be 16 to 3, 48. Right? 48 into 10 to the power
10 power
minus
minus 7.
7 meter cube per second per meter length of the earthen dam. Okay.
Yes.
Okay. Was this question good? Something,
Yeah, it was good, sir, but only why I neglected, I didn't give a much focus is the time may not be enough for GATE type of exam, but IES and university exams is very
yes,
important.
yes, yes. This time, this sum is actually very, time taking. Generally, civil
Time, yeah.
services, engineering service examination, this kind of problems might come. Okay.
Okay, so.
Next question, I
This
think.
one is, sir, I told actually Cogeni's formula, something this one, I think.
Which one?
The K is equal to S, K into S is equal to discharge. This formula,
Yes,
we have
yes.
a name for this. Is
Yes,
there?
Cosinus formula. Cosinus formula. Yes, yes.
Cogeni's formula. That only
Cosinus
I told
formula.
at the beginning.
Oh, you said at the beginning,
Yes,
Cosinus formula. Okay, okay. I might have not heard it. Yeah, Cosinus formula, I think. Yeah, I have to check, but I
thank
think it is
you.
Cosinus formula. Okay. Yeah.
Yes, sir.
Okay. So this one, I think this one is recorded. Yes, recorded. Okay, fine. Next one, you have solved this. Have you solved this question?
Yes, sir. I have done the answers. You can check it.
What is the answer for the first scenario?
First answer is 0.6366, sir.
Yes, 0.64. Very good. Then the second answer is
0.51.
0.51. No, no, no. Okay, wait.
No, sir.
No, wait.
I will check.
Okay. So sigma z, what is the formula? Sigma z equals to q divided by, I'll just write it in a simpler way, pi z square, okay, in bracket 1 1 plus 2 into r by z whole square whole to the power, this whole to the power 3 by 2. Okay. Now when r equal to 0, okay, this becomes, sigma z becomes, q by pi z square, isn't it? This is easy. So 200 by pi into 100, I believe it is 0.64.
Yes, sir.
Yes. Now when r equals to 2, solve it when r equals to 2.
It is a second answer is 0.419.
419. The overall answer. Okay, just do one thing. Just a moment. Z is same in both the cases. No, Z is not same. Z is different. Here
That is
this
5 meters. Okay, okay,
here
that's a mistake I
yeah,
did.
yeah,
Okay,
that
okay.
is. I also doing the same mistake like you, but in the first case scenario, Z is 10 meter. In the second case, Z is 5 meter. So putting Z equals to 5 meter, Z equals to 5 meter.
Is it 1.67 is okay, sir?
Yes,
That's
yes.
also wrong.
1.68, 1.67, something like that. Yes, it will be
Right.
approximately 1.68 kilo Newton per meter square. Okay. Z equals to 5, R equals to 2, and previously it was Z equals to 10, R equal to 0. So clear, right? This is the basic Westergaard formula. Okay, again. Just a moment, huh? Again the same problem like yesterday. I'll check once. Anyway, I had to close it yesterday, right? And again open it. I think I had saved
If you
this.
close, you have to do all of this once again.
No, no, I think I have saved this in the last.
Okay, up to some slides.
I'll do one thing. I'll open a new slide, blank presentation. I'll open a new blank presentation because the last sum was very tedious.
Yeah, it takes time.
So what I'll do is this solution from here, this one and this one, I'll just copy it to a new PPT. Okay, like this. Even if the format is wrong, no issues. I can just copy paste the thing. So don't save. I'll open it once again and see where I've saved. Okay, I have saved till the previous one, and the thing I have not copied, that got deleted. Anyway, I'll just name it as something extra. Okay, so this one I'll just save it once again. uh, what was the formula I have used? Just tell me fast. It is sigma z equals to q divided by pi z square.
Sir, can you share the screen, sir?
Oh, okay, okay, fine. Yes. Okay, right. 1 plus 2 r by z whole square whole to the power. Is the screen being shared? Can you see the screen now?
Yes, sir. Yes, sir.
Yes. So first scenario, r equal to 0, z equals to 10, sorry, z equals to 10. So the value of sigma z, putting the value, will be 0.64 kilonewton per meter square. And the second scenario, r equals to 2 and z equals to 5. So in this case, sigma z will be equals to how much? 1.68,
6, 7.
yeah, 6768 kilonewton per meter square. Okay, save. Okay,
Yes, sir.
and from the next sum, it won't be any problem because I think I have given the solution over here only. Yes. Have you solved this question?
I think the answer is 16 divided by 9.
Yes, very good. So the anisotropy ratio is basically kx by ky. Okay. So before the transformation, okay, uh, it was 4. After it was 3. So you solve this and you get kx by ky value 16 by 9, 1.78. This is the answer, right? 16 by 9, 1.78.
Yes, sir.
Yes, good. The last question. Have you solved this?
Uh, 1.5 into 10 power minus 4.
Let's see. Yes, very good. So you have used this formula for finding out the value of k.
Yes,
100
sir.
d10 square, very good. So this was not given, the value of k.
Yeah.
Sometimes people ask, why is the value of k, how can you find out? And this nf by nd was given in a reverse order. So it was given 2, nd by nf was given 2.
Mm.
Just
Yes, sir.
transform it, numerator and denominator, k 100 into d10 square, h is 3. So this is the value. Okay.
Yes, sir.
So this brings us to the end of the session. Any query, any doubt regarding this?
No, sir. Thank you. Today I have updated some additional points. Mistakes I have done. Through that also I improve.
Okay, okay, fine, fine. So this was helpful, right? This session was
Yes,
helpful.
sir. Helpful. Definitely, it will be
Yes.
helpful.
So I'll just clarify one thing from you, because you have been, I think, in all the classes on the sessions of mine. I think
Yeah.
till session 9 has been completed. Today was 8, yesterday 9 has been completed, isn't it?
Yes, sir.
So I
Yes.
think 3 sessions are left, and after that I'll be asking for a summary session, you know, for
Yes. Yes.
everything. So I'll just you will be notified about the summary session after the session 12. So 3 sessions are left, right? 10, 11 and
Yes.
12.
Mm.
So okay, we'll again meet on the coming Friday. Okay, thank you for
Yes,
attending
sir.
the class. Have a good evening.
Thank you.
Okay,
Thank you,
yeah,
sir. Thank you. Good
yeah.
night.